Okay, and I'm from Humboldt State University in Arcata, California, and I'm here to talk about testing gravity on small scales using a precision optical system. And we're doing gravitational research at HSU, and the second talker will also provide references for my talk. So right now, gravitational physics is in a golden age. There's a lot of experimental research that can be done that is probing new areas of physics that can. So right now, the question is, why are we studying gravity at small distances? And one prediction in cosmology pertains to dark energy. There's theories out there that say that at small scales, there's deviations in the gravitational force, the inverse square law. Also, there is string theory that talks about extra dimensions being curled up in small distances. The distances we're looking at is like 1/10 of a millimeter. So in small distances such as that, there's theories that predicted there could be extra forces required involved in gravity. There's also possible unknown quantum effects due to new forces and new particles, and that's yet to be discovered if that's the case. There's also a lot of prospects for gravitational research that we're doing. There's gravitational waves, a lot of experiments searching for gravitational waves right now. LISA, the space-based one that should go up in a few years, I hope. There's also LIGO and Virgo and some other ground-based interferometers that are searching for gravitational waves. There's also what we're doing, which is laboratory tests of the inverse square law, and also looking at the equivalence principle. Also, there's astronomical tests of general relativity that are going on, which relate to gravitational waves and other things. So large-scale gravity is studied in cosmology, and we're looking at small-scale gravity. So what we're looking at is deviations in the Newtonian gravitational force. So the equation on the top has two terms. One is the standard gravitational force potential, and the second term is the Hikawa potential, which is what we're looking at. Different terms relate to like the strength or the distance involved. And so this picture right now is the current research for the Hikawa potential. Is sort of the yellow region is the excluded regions that have already been taken off. The University of Washington produced the most significant amount of research in order to exclude that region. Anything below and to the left of that is where we're probing, which is very difficult because it involves small distances or very small forces. And so right now until recently there's hasn't even been shown to exist for less than a millimeter for gravity. So what we're using is a torsion pendulum. That's the most sensitive instrument that can be used to date for this kind of research. So what we have is a thin fiber, and it's going to be in this case, this has two masses on a string, and as you bring a larger test mass closer to it, it will provide a twist, and if this test mass is oscillating, going in and out, then it will provide an oscillatory twist. So that's what we're actually going to be looking at, and it's very sensitive to small twists. So that's the reason why we're using it, because we need very, very precise equipment. Our apparatus right now is, there's a lot of noise that is involved in such small scale tests. Gravity is very, very weak. So we have an apparatus that is thermally isolated, and that will that produces any changes in temperature that it isolates it, so that way we don't have to deal with any sort of stretching or shrinking of our apparatus. We also have a vacuum chamber in which we have our pendulum in, and what we're doing is we're bouncing a signal into the chamber through a hole in one of the flanges. And it's going to bounce through some mirrors, and it's going to bounce off our pendulum. So what we have is our attractor mass is going to be oscillating, and what we're looking for is any twist in the pendulum that will be reflected through the laser, and it'll go back into our optical block. So so far we have the apparatus set up, and we've been doing tests on different hanging pendulums and stuff like that. We haven't had our real pendulum up yet, but we're doing that right now. So what we have is a large attractor mass, and what that does, it provides a uniform Newtonian gravitational force, and so hopefully that won't even show up. What we're looking at is, because it's such a uniform force, we're looking for any deviations due to small forces. And so our pendulum is a stepped pendulum, and that will provide, essentially what we're looking for is, as we modulate our test mass, it will provide a twist on the pendulum. One side of the pendulum is closer to the test mass, the other side is further. So we're looking for any small deviations that are provided from that small distance. So hopefully because we have such small distances, we have to look at things like quantum effects, like the Casimir effect. And so at that small distance, we might have forces that will show up as a tweak of the pendulum. So we have to provide a very thin, stretched metal membrane, and that will hopefully isolate that and make it not an issue. So our optics block consists of a beam, a laser beam that's going to go out through a lens, and it's going to go into the vacuum chamber. And as it comes back, any twist in the chamber, in the pendulum, is going to show it as a change in the laser spot. And on the right-hand side, we have it's actually a position sensing detector, and that's what we're going to use to detect the position of the laser. So it's going to bounce in, and then it's going to bounce out. So we have a sort of periscope style mirrors, and it's going to bounce through and hit the pendulum. And then we can figure out with some simple trigonometry what that deviation is. And we're looking for nanoradians as our sensitivity. So there's quite a lot of effects that can swamp the gravitational force at that distance. So our autocollimator is what the optics system we're using, and this is the position sensing detector. It's a very simple slab of silicon with 4 connections on it, and so as the laser hits it, it will provide it will send a current, and the current will go to all 4 sides essentially. So the closer it is to one side, there's going to be more current, and so we're going to, with a very simple math, we can figure out the position in the x and y, and we're pretty much concerned in the x direction. There will be possibly some deviations in the y direction, but mainly we're looking for a twist in the x direction. So that all 4 channels go to instrumentation amplifiers because the signal is so weak, and then that actually goes into our data acquisition system. And so we have an elaborate setup in order to analyze the data. So once we get the data in, what we're looking at is, right now we have a lock-in amplifier that we're using, and that significantly reduces noise. What a lock-in amplifier does is it provides a reference signal at the same frequency as our laser pulse. Our laser is being pulsed at 10 hertz. So we also have a reference signal at 10 hertz, and what the lock-in does is it looks for signals that are along the lines of 10 hertz, and there's a lot of stuff like electronic noise from lights and things like that, and that should hopefully not show up since it's 60 hertz. So it's going to filter a lot of noise out that would be a problem in our readout. So there's still going to be noise, but it'll be a lot less. So we're currently using LabVIEW because it's the industry standard for this kind of thing. And it's really nice. It's a graphical interface. So instead of using code, we're basically just literally wiring these elements up. And so it's kind of attractive in a sense. And the nice thing is it provides a good user interface. And so when we're looking at our data, like this is what we see our laser spot essentially. So we can actually see it transversing on the screen as well as